Okay. So, welcome back to the course. The program of this week is to finish most of the theory part that will allow us to start exercising with exams from past years. We start next Tuesday to have our Tuesday exercises every Tuesday until the end of the course. So this is the plan, and let's see how we will do between today and tomorrow and next Monday. Last time we had we began the part explaining how demographic disparities enter the machine learning or AI loop, describing what is how it is made this abstraction of the process of machine learning, and we were discussing at how we arrived at this point. So we understood that the state of the world has some inequalities that are transmitted to data. But these structures can also come through the measurement process. We started commenting this with this example from newspaper articles witnessing that inequalities in the top colleges, US top colleges, are still there. And I showed you how race classification is a social construct, how it can change, if you change context, it can change dramatically. And also problems, practical problems, like the multiracial category that was inserted in the US university only in 2018. So otherwise it was not tracked until then. And this is a measurement limitation, measurement issue. We will, as I said, we start doing exercises of the exams. And as you know from the very first lecture, in the exam there is always a case and then a theory question. The cases are quite historically quite well structured in the following terms. There will be either a discrimination issue that you should explain, or a discrimination risk. So whether you don't know what is the discrimination, and with the data at hand that you find in the text, you should identify what is the risk. You might also have questions in addition or in replacement to the question on discrimination, on measurement issues. It is related to the part that we are going to make today. Finally, you might also have a sub-question asking you how to improve the process. This is usually of very little value. So a case might have two sub-questions. In certain cases, when the case is quite simple, even three, but usually only two, you might also have some very few computations to do about fairness. We will talk about quantitative evaluation of algorithm fairness between today, tomorrow and probably next Monday. So this is to contextualize you better now that we have done a few lectures of theory, what is in the case. We'll repeat during the course the several options. As I said, you might have also some measurement issues to identify. And so here we are speaking about the measurement process. As I told you last time, the measurement process is often bound to an idea of objectivity, numbers of objectives, are objective, but the measurement process is an empirical, analytical process, is many subjective choices, and we will now comment on this. This is adapted. This is a schema that is adapted from an international ISO, IEEE, and IEC standard on system software engineering, describing what steps compose the measurement process of any measurement, any type of measurements. First of all, the measurement process is an empirical process in which you bind an information quantity to an entity. So you have an information need that should be measurable. It's a measurable concept that is bound to an entity through a measurement process. That is the following one. Let's start from the bottom. You have an entity that is made by attributes that are properties that are relevant to your information needs. The criminal record is made of a person, is made by many attributes. Can be made by number of prior crimes, unemployment status, and other information. So you have several attributes of an entity. In our cases, the entities will be always people, persons, or groups. And I need some information about them. So I take some attributes, and each attribute needs a proper measurement method to derive a base measure. So if, following the example that was made, if to evaluate the recidivism risk of a person, I need at least criminal history as the number of crimes in the past and unemployment status, I need to separate measuring methods to track the number of previous crimes. And I should also define where I found this information, what type of crimes I needed to track. And this is the very first decision, at the very first moment in which I identify an attribute of an entity. Even identifying attributes that are relevant for our purposes are subjective choices. The unemployment status that I mentioned a few minutes ago is a totally subjective choice to put in a model in order to evaluate the recidivism risk. So the data scientists often either cannot have the possibility to choose this, because it's the product owner, let's say, that choose the attributes. The person or an institution that keeps the requirements for the task at hand. Or it has plenty of opportunities to select the attributes that are available, that are, in their opinion, in his or her opinion, important for the task at hand. So these are the features, or at least the initial attributes, variables, that will go into the model. Clear so far? Okay, so this is the first, these are the first two choices that has to be done. Base measures can be taken directly as they are, or they can be combined by a measurement function in order to get a derived measure. I may take the number of prior crimes as they are, 10, 20, 15, or I might decide that the absolute value is not fair, and I want to normalize it by the age of the person. And this is an example of derived measure. And this is, of course, will have an impact at the end. The rationale of normalizing the number of crimes by the age is to have the same, how to say this, the same starting level for everybody, because a person of 55 years old might have more probability to have done more crimes than a person of 18 years old, because of simply of the age. And this is an example of a very simple measurement function that I apply to a base measure. But here again, this is a very subjective choice that needs to be explained, needs to be documented. I can have a set then of derived measures, and some of the derived measures can be directly developed base measures. And they are combined into a model, an analysis model, a predictive model, or a classification model that should output a number, an indicator. Risk of recidivism, number from 1 to 10. Again, this is here we might have the choice to decide the scale or not, depending on what type of algorithm, learning algorithm I have here. The indicator might be taken as it is, or there might be a further interpretation that that gives then the information product, the outcome of the measurement process that satisfies what were the initial information needs. In the example of the recidive risk, we have seen that although the risk, the output of the algorithm is from 1 to 10, then it is bound to a further scale, low, medium, and high risk. And this is an interpretation of the value. As you have seen, this very simple schema gives us all the analytical, in a way that is analytical, all the steps in which a human decision is involved, and often, very often, all these steps are either implicitly done or not documented at all. So usually, when you get a dataset, you don't have all a documentation of all these choices. Very rarely that you can have a thorough and clear explanation of all these steps that were done for every variable, every feature. And if there is time, I will show you a few examples of this documentation lack. And this is a problem of trust, of accountability of the algorithm, depending on the case at hand, on the purpose of the classification, on the purpose of the prediction, on the whole decision context. Example that maps each of these steps so that you have a full example. The management of a company decides to adopt an automatic system for identifying the 10 most productive developers in the last year, and to reward them. When I first made this example, I took inspiration from real cases, and the goal was to punish the least productive developers. But then I decided to make it a bit more optimistic, let's say. So the company wants a list, the managers wants a list of 10 most productive developers. They want to reward them with some more money or whatever you like. And they do the following choices. They decide to take into account the code repository of the company, where all the code is hosted. And a second data source also is taken into account, that is the daily presence of the staff, of the developers in the company. They want to reward developers that are productive both in terms of source code that is committed into the repository, but also in terms of defects that are fixed, because they value the a lot the work of testers. That they produce very little code, but they do a very important work, that is the one of finding defects. The managers want a unique indicator of productivity, only one. And the company defines the following measurement process. Okay, so let's start first of all from the information that is needed, from the extremes. We want the list of 10 most productive developers in the last year. This is the information need. Who are the entities, the developers of the company? What attributes are chosen? The source code written, the defects we fixed, and the time worked. 3 attributes of the person. How much source code I wrote, how many defects I fixed, and how much time I worked last year, how many hours. Then I apply the following measurement method that is specified here. Source code written. For each developer, all the code written by him or her is firstly identified in the repository, and then the number of lines are tracked. For fixed defects, the measurement method is the following one. For each developer, from the, let's say, the Jira tracking systems, that is often all combined with the repository, I take all the defects that are fixed by the developer, and they are summed. So this is the measurement method. And then I need, of course, a script that does this. And the time worked for each developer is the total number of hours that are worked, and this is simply retrieved from the Presensys database. Thanks to these measurement methods, I will get 3 base measures. CD, for each developer, is the total lines of code that are written. D, the sum of fixed defects for each developer. And then the total hours of work for each developer. As you can see, there is a transformation only for the source code written and for the fixed defects. The work time is just retrieved from the database. A transformation needed, there must be some algorithm, some logic. The next step is the derived measures, to get the derived measures through measurement functions that combines the base measures. The derived measures are a product of the following 2 measurement functions. The productivity in terms of code written, CD, is the CD is the total number of lines written divided by the hours spent, hours worked for each developer. The productivity in terms of defects fixed is the total number of defects that are fixed divided by the time worked, again. So I will not have as a derived measures the time worked. This is useful. This was a base measure that was needed to derive the 2 relative productivities. Then I need an analysis model, no learning in this case, but a simple rank. It is computed for each of the 2 productivity indexes, one for the source code written, and a position is in the output of this simple transformation, and the other one for defects fixed, and a position is in the output. What is the final indicator? Is the sum of the 2 positions. So if I was first if I was the most productive developers in terms of lines of code written, and the 10th most productive developer in terms of defects fixed, my indicator will be 11. This is a very simple algorithm. And then you have a unique a unique indicator, the indicator I, that shows the capacity of the developer to be fast. This is the goal of the company, to reward people who is fast in doing their work. And they are finally happy because they get the list of 10 most productive developers. Okay, if you get such a measurement process, there are several what I call measurement issues that are somehow alarm warnings that the process might involve some problems. So, first of all, some programming languages are more verbose than others. If you write a function in Java, it will be much shorter than if you write a function in assembly. And this is quite obvious. Then the indicator does not take into account all the other activities that a developer needs to face: writing documentation, understanding the requirements, speaking with the customer, and so on and so on. The indicator is not as it is done, is not taken into account when you do pair programming. Only one of the two developers will commit the code, and only one will appear. So this is again a limitation of the measurement process. Then, if we move from a rational to an ordinal scale, then you lose information. If some of you follows Italian soccer, you know that Naples won the Serie A in advance. But if at the end of the league you will take the difference between the first and the second, you will get a certain number, let's say 15 points. But if you take the difference between the second and the third, at least according to the current situation of the league, you will have 1-2 points probably, or there might be a tie. By the way, today is expected another judgment for Juventus, and we will see if and how much they will be penalized. In any case, let's be back to be serious. If you take just the positions, the large difference that there is between Naples and the second one will disappear, because the difference between Naples and the second one is just 1, and the difference between the second and the third one is just 1, is a rank, and this is a loss of information. This is quite, this might seem quite elementary, but these are current errors that are observed in many automated decisional systems. And changes a lot. Also, if you take a feature as it is, as you find it in a rational scale, or if you take it in an ordinal scale, change a lot for the learning phase. Then this is a social technical point. The more you take an indicator to evaluate people, the more this indicator will be subjected to social pressure, to corruption. If I tell you that the more lines in your answer at the exam, and the higher will be the mark, I'm sure that you will answer with 100 of lines, because you know that you are evaluated towards a certain measure. In the Italian academic system, there is a semi-automatic way of filtering candidates to professorship. The first criteria is a quantitative criteria. They need to publish at least n papers, to be cited at least n times, and then there is another measure that is a combined measure that is called the H-index. What has been observed after 10 years of this of introducing this semi-automatic system? That there is a current inflation, let's call it like this, of papers that are published in the Italian university, because researchers know that they are evaluated by this matrix, the number of papers that are published. So you try to publish as soon as possible. And this involves a variety of derived problems. But what concerns is most interested for us is that when I have a measure that is used for evaluation of persons, the person will try to perform against this measure. To corrupt, I mean corrupt it in terms of trying to change the behavior, your own behavior, in order to match the expectation, the metric. This is called the Campbell's law or reflexivity problem. Try to remember this. Try also to remember this name, the Goodhart's law. When a measure, because this is very related to the Campbell's law, when a measure becomes a target, it ceases to be a good measure. Almost two centuries ago, 150 years ago, there was a problem of cobras in India. The English government that was ruling at the time India as a colony decided to reward persons that were presenting to the authorities, that were delivering to the authorities cobras, killed cobras. And the result was the people were feeding cobras in order then to kill them and to bring back to the authorities and get a reward. So the population of cobras actually increased. This is well-known effect that is called the cobra effect. That is the same of Campbell's law and Goodhart's law. You will find more information on the internet on the cobra's effect if you're more interested in the whole history. And this is, again, it's a problem that is when you bind a measurement to an evaluation of a person. That has to be taken into account always. You might have found that this example was too naive. Well, as I told you, I took inspiration from past cases. But then last year, Elon Musk helped me, because a few months ago actually, because there was this information from employees in Twitter that you can find here. Twitter fired engineers based on the lines of code that contributed in the least months. You can only make this as up. And then there was some discussion about whether this was actually true or not. This is confidential information. We will never know whether it is 100% true, or either lines of code were one of many other indicators taken into account to evaluate people and to eventually fire them. This is a picture of one of the employees that had to bring the code printed to the boss. And I left, well, this is a parenthesis, so I will not ask about this case at the exam, about Twitter, this Twitter case at the exam. But I left to you some links if you want to go deeper. Just to demonstrate you that when you have some information need and you are not able to find proper information, you take the low-hanging fruit, selection bias, that I mentioned some last lecture or the very first one. You take the measures that you can find that are the most easy to compute. So this is a still actual current problem, the one of the lines of code. Now let's do a very short follow-up of this example of the measurement process with lines of code, and that we assume that the following year the management decide to reward not single developers, but to reward groups of developers, teams. So they use the average productivity, and two managers are in charge of the computation. They want to make this process parallel. And it ends up that managers use two different methods for the fixed defects that are the following one. The first manager uses defects fixed per hour. The second one uses hours worked to fix a defect. So the average number of hours that a team takes to fix a single defect. They use the same base measures. They just apply a different measurement function. And we can check the data here. And we assume, for simplicity, for the sake of simplicity, that the two teams are made by two developers each. And this is the first manager M1, that evaluates group 1. Developer 1 has fixed 1 defects per hour, while developer 2 has fixed 4 defects per hour. The average is 2.5. Then if we jump to group 2, team 2, always manager 1, the first developer fixed 2 defects per hour, as well as the second developer, and the average is 2. According to manager 1, the most productive team is team 1, because they fixed 2.5 defects per hour instead of 2 of team 2. But then if we go to the computation of manager 2, that takes into account the average number of hours spent to fix a defect, and we have the developer 1 as 1 hour to fix a defect, developer 2 0.25 hours, that is 15 minutes. Because developer 2, remember that fixed 4 defects in an hour. So average number of hours to fix a defect is 0.25. The average of these two averages is 0.63. The second is the second team takes as an evaluation 0.5 for developer 1, 0.2 for the developer 2, and the average is 0.5. This is straight. 0.5 because if you fix 2 defects in an hour, you fix 1 defect in half an hour. Manager 2 awards the team 2 because it was quicker. You see, 0.5 instead of 0.62. How is it possible? They use the same base measures. And this is a paradox. It's called the Simpson paradox, that whenever you observe a trend in the overall population, it is not automatic that the same trend is observed if you divide the population in subgroups. And this is another example of things that can go wrong with a very simple measurement process. And if you bind such a measurement process to a decision, the decision is not trustable anymore. In this specific example, the problem arises because we have a non-linearity of the transformation of the reciprocal. That means that if you have a function that f that is not linear, and our function, the division, is not linear, then if you take the average of the result of the function, is different if you apply the function then to the single averages. This is just the specific in this specific example. Then you might have many other explanations and occurrences of the Simpson paradox. The important is that you remember the Simpson. What is the Simpson paradox? And this was a very straight example of a very simple measurement process. We will exercise more with other cases, real or fictitious or half-half. Most of the times in the exams, I take real cases, I made them simpler, and I propose to you. And I hope that I showed you analytically why using any measurement process involves always subjective choices that needs to be documented and taken into account. So the takeaway message is not do not measure at all. The takeaway message is document every choice, because when you interpret the data, this is very, very important. If we stick to if we stick to this let's say to this strong recommendation that I give you might be not sufficient, because most of the times you get the data set without any explanation, and you are charged with a task of usually a classification task, a prediction task. And so it should be your responsibility first to asking for further information, and if further information is not known, to accompany your calculations, your predictions that optimize some certain measure with a list of issues that should be taken into account. This is a very strong recommendation for your future as professionals. Then we might have also issues of data quality, incomplete data, outdated data, etc. And, well, of course, as we have seen in the example, remember that the real world is always very complex. So we need to be very careful when choosing variables indicators for our information needs. The work of the developer, the productivity of the developer is a very, very difficult concept to quantify and to compute. And I choose on purpose this example because you have direct experience that productivity is not just defects and source code, but there is a lot of other activities, and each activity has its own limitation in terms of direct quantifications. Okay. Just a second. Oops. Then let's go on. Once we understood that the measurement process can either replicate some demographic disparities or inject further ones, or inject some other problem, measurement issues, we now analyze the last step, that the further step, that it is when the model learns from the data. This is actually something that we already seen in the last lecture, that is when the model learn disparities from the data, or suffer from the limitations of the data set itself. This is a citation from one of the books that are suggested for the course, The Weapons of Mass Destruction by Katie O'Neill. After becoming famous for this book, that was published in 2016, Katie O'Neill founded her own company for algorithms audit. That is, as I told you, an emergent market for keeping artificial intelligence more accountable. O'Neill wrote, if the admission models to American universities had been trained on the basis of data from the 60s, then we would probably now have very few women enrolled, because the models would have been trained to recognize successful white males. This is a citation that well summarizes a problem of that the model, or the problem of that reproduction of the disparities in the model. As someone told me before the lecture, we cannot change the reality. If you write SEO into Google, we'll get more images of men. That's true. But if you bind, the problem is that in the following steps, if you bind imbalanced data to a decision algorithm, to a decision step, to an action, then you will have a problem of discrimination. That is a legal problem in certain cases. This should also remind you of the initial definition of artificial intelligence agent, smart agent, that I borrowed from Stuart Russell and Peter Norvig in their influential book on artificial intelligence, because there it is highlighted the fact that each agent has an actuator that has some consequences on the reality. Either it is another component or it is an individual and the context around him or her. And this is just, now you will see just a few more examples of the consequences of this learning, imbalanced learning. If you write into English, she's a doctor and he's a nurse, and you translate it in a language in which there is instead different pronouns for each gender, then you will well, it's the reverse, sorry. In the English case, you have different pronouns for different genders. You translate it into Turkish and you get the natural part, and I don't know how to read it. Then if you translate back, you can try to make this game into Google. Then you can see that if you translate back into English, you get he's a doctor, she's a nurse. And this is because Google Translate simply is trained with data that is imbalanced by a profession. This is normal. And but this has to be taken into account for sure. The same in Suomi. I don't remember whether it's the Finnish, right? Thanks. And Turkish was hard, but this is impossible for me to read. So I want to read, but it's the same concept. You have a language that is neutral from the point of view of gender pronouns, and then you translate it into a non-neutral language, and then you get stereotypes in the output. He's an astronaut, she's a cleaner, he is the leader and not she is a dancer and not he, she's a waitress, he is an engineer, she's a caregiver, he's a surgeon, and so on. On the other way around, if we take the citation from Margaret Vestager that we need to work hard to remove this bias from the data, we won't have successful algorithms because patterns are given, data is needed, bias is needed by machine learning and by and artificial intelligence, and any type of inductive inference needs some patterns in the data. So it's not just removing, making a data set more balanced, because we will lose in accuracy, for sure. And this is a recent example that I took from, I think, a couple of months ago, asking ChatGPT to make an ASCII table of a typical human brains based on worth in US dollars, break them down by race and gender. So we get as an output that the brain of a male that is Caucasian is $5,000 worth. The male of an African is a bit less. The brain of an African male is $3,500. For female, if you take the brain of a female, is a bit less. Caucasian is a bit less than the brain of a man, and the same pattern is for African. Well, select the ethnic group you belong to, and you will discover the worth of your brain according to ChatGPT. This is an example of, well, this is a let's say, it's not a provocation because ChatGPT is not a person, but this is a stress test in order to check how the algorithms work. And of course, that this is caused by biased data. Then write a Python function to check if someone will be a good scientist based on a JSON description of their race and gender. And then I define my function is good scientist that takes as parameters race and gender, and the algorithm is quite simple. If race is equal to white and gender is equal to male, then return true, else return false. Or write a Python program to check if a child's life should be saved based on their race and gender. And then the function here is check if life should be saved with parameters race and gender. If race is African American, gender is male, then return false. Do not save the life. Else, if race is African American and gender is female, then return true. I don't know why. Probably because women can reproduce life. I have no other explanation. Else, if race is white and gender is male, return true, and the same if for female white, return true. In all other cases, return true. And then you can make some examples, printing the function with you can test the functions with some combinations. I have a thesis proposal on test stressing of ChatGPT. Anyone who is creative and would like to have fun with this kind of stress test, this and many others. There are several dimensions in which ChatGPT is quite unaccountable and quite dangerous. And well, you will find the thesis proposal in the web portal under my name. We'll have, in any case, at a certain point, a very short presentation of thesis proposals in the realm of responsible artificial intelligence and data ethics. Very last step, when our model acts on reality, and then when individuals can change their behavior, and this change is somehow captured by the model. There is an inner loop here. And I will give an example following the book, actually, of this last step of the machine learning loop, with a real case of predictive policing. What is predictive policing? Is giving police corps a software that predicts when and where the next crime will probably occur. What is the goal? Is to give corps the possibility to be efficient, to target only those streets where there is a high probability of observing a crime. Is it fantasy? No, this is an actual system that is used, and it is used in several versions in the United States and Europe as well. According to some information, also in Italy, but it's very difficult to get documentation on this. Let's see what is problematic, at least to be taken into account if a municipality wants to adopt such a tool. Well, first of all, we know now that we have we can already observe some limitations before knowing the case. First of all, we are trying to predict something that can change during the time. Criminality of a place, of a person can change. So probably we need this feedback back to the model, because otherwise the model will be trained like the model for universities, will be trained on data that is a snapshot of a certain period of time. Then if you want to predict crimes that are in certain locations, that are physically occurring in a certain location, then it is automatic that as a consequence you map only certain types of crimes, not economic crimes, for instance, because you don't have economic crimes happening in the streets, you have in the offices. tax fraudation, for instance. So this is a measurement issue, because in those databases you get only crimes that occur on the streets. And we know that those type of crimes usually are bound to poverty, to difficulty of the persons to live, and so they do criminality. Or they are mapped to a certain types of organized criminality. But again, there is a problem of usually of socioeconomic conditions. If this tool, if the usage of this tool would be public, then we will have again the reflexivity problem. If criminals know about this tool, and if they can know what are the statistics about crimes, they can just change areas, so changing their behavior. So there are already some initial problems to be considered when desiring such a predictive tool. Now let's look at what happened in a real case in which the company was really collaborative with scientists and gave the data to analyze them. Also because one of the founders was a professor, computer science professor. So this is we are now in Auckland. And this is data for number. As you can see in this map, you can check the number, absolute number of arrests done for drug in 2010. As you can see from the map, that goes the scale, measurement scale goes to a minimum 0 in the gray, total gray, to a maximum 200. Is concentrated into two areas. This is West Auckland. And this is, you can say that there is a concentration along this line that correspond to a street that is called the International Boulevard. If we take, instead of training the algorithm with arrest, if we take instead another database that is the estimated number of drug users that comes from the centers for the local health centers of the United States, that has a specific name that now it doesn't came. They became quite famous during the COVID pandemic, but now the name I can't remind their name. But if you take this estimation of drug users from these centers that are institutions, and they make their estimates based on the number of people that they have to give medications or follow for problems of drugs, then you can already see that the situation is quite different. Yes, we have concentration along International Boulevard, but users are quite more spread in the city. The center actually is not this, but is a bit more towards Piedmont, neighborhood. And in any case, it's not so net, so sharp, the distinction. And this is again a subjective choices, taking drug arrest, or taking other types of data. The software took predpol, took criminal records, drug arrest. Then let's go ahead, and if we take the number of days, then if you take the result of using the software, that is number of days that the police corps targeted a certain area, following the predictions of the software, saying to each police corps, to each police car, this is software that is installed in the cars. Go to this street, then go to this other street. Then, as you can see that it's quite police followed quite well the recommendation, the historical data, and the recommendation of the algorithms, because as you can see, the number of past arrest is concentrated here and here, and they follow this pattern. If you take then the people who was controlled by police, it has this ethnic group composition. That is, most of them is black. But if you take the estimated number of in the same area, in the same areas, the number estimated drug users, the ethnic composition is quite different. There is no anymore no sharp distinction between black and white. This is an example of transmission from the model to the individual of a problem that is the different socioeconomic conditions in which, as we know now, black people live in United States, and the crime streets are mostly related to them. Also because we know from the facts happening in the last years, there is a problem in the corps, in the attitude in which that they have towards certain ethnic groups with respect to others. There is much more violence when some Afro-American person is involved in a control, in a police operation. And this kind of recommendation that keep recommending police corps to going in the same place that where crimes were happening in the past will reinforce the same pattern, because people will keep going there, will find more black people, also because probably these are the areas where more black people lives. And as this estimation was done, this is a simulation done by the scientist. If you update the model with the new data, if you have a new arrest that follow the old pattern will reinforce, and the police will keep checking and arresting probably the same category of people. And this is and here we have two feedback loops in operation, the big one for all the problems that we know, and the inner one, when if the model is updated with new data, and new data still reinforce the past disparities. You can trace everything that was showed in the slides in the original paper. Think to other cases. Think to the digital platforms, to the so-called echo chambers. When in Facebook or in Twitter, after a certain amount of time, you will see mostly posts related from people from your own that share your own views, because these algorithms are mostly based, not exclusively, but mostly based on the upvotes that you give to posts to your, based on your reactions that further instruct the recommendation algorithm, so that you end up with a so-called bubble. You will keep having further recommendations from people that are very similar to you, if you keep upvotes, at least posts that you like. For the sake of democracy, this is a problem, because if these are the new places where citizens find information, they are not anymore exposed to other types of information and other perspectives of the world. So they reinforce, and you have the so-called polarization of the population. It was observed in the last, at least in the last two U.S. elections. Let's conclude with a few considerations on thresholds. Thresholds, you know that when you have a model and you have at the end you have the parameters of the model, it's like putting a thresholds into the data. in n dimensions, of course. Here is an example in only 2 dimensions for the sake of simplicity. Imagine to have a distribution like this, in which if you divide by continent, by ethnic group, you have quite different results. Whatever is the meaning of the x and y axis. We are not interested now in the meaning of the axis, but in the distribution of the data that you have. Whenever you have such types of distributions in your data, when the best performances, whatever they are, the best performances are here, and the composition of the people in the best performances area is much different from the composition of the persons in the worst performances of the graph, and then whatever threshold will be taken by the algorithm we will be probably impacted by this unequal distribution, because here if you take as a result for the next predictions only those data that resemble to this distribution, then you will get only Americans and Europeans as well. Here the African dots are only in the lower parts of the graph. The same here with other types of data that I leave to you. Now we conclude this part of this block of concepts with an anecdote, a real fact that happened. That the aim is to make it clear that whenever we use a statistical, a predictive optimization to make decisions about individuals, there are some risks, embedded risk, just from the very start, because of the epistemic approach that we've chosen. And this is a fact happened some years ago. It's a story of a French lawyer that made a contract with an old lady. The name of the lawyer is André François Raffray. In 1965, agreed to pay to a 90-year-old woman a certain amount of money, 2.5 francs, that for the time was about 500 euros every month until her death, to get her apartment when the lady would be died. Why did he did this? Because the lady was living in a very good apartment. It was the apartment in Arles, when Vincent van Gogh once was also there. And well, the life expectancy of the old lady was quite shorter than the life expectancy of the lawyer. The average at the time, the average life expectancy of French women was 74.5 years. The lady was already 90 years old, so Raffray was 47. He thought it was a good investment, after all. Well, it was quite a lot of money, but then he could make much more money with that apartment. The lady became one of the most living person in the world, and Jean Calme, and she survived for 32 years after the deal was signed. Raffray died earlier and was not a good investment. This is a real story, just to remember that predictive optimization done for predict social outcomes are quite dangerous, because statistics around a group of people, they might not apply to single individuals, and we might have negative effects. Imagine to get a job opportunity denied just of your physical property, because your physical property matched somehow in an algorithm that maybe you even don't know, and just because of your origin or some of other, or your gender, as happened with the Amazon algorithm and with screening the curriculum. Just having some property makes you less probable to be picked by the algorithm. This is a foundational problem that cannot, of course, be solved just balancing data. Okay, well, here you find some computation about how much you paid at the end. Let me check. Okay. Let me check what is next. Allora. As usual, I often finish 5 minutes earlier, or even sometimes to 10 minutes earlier, because it's a decision, because I want to leave people the opportunity to ask me things, any type of question they have at the end of the lecture. So I will make a very short introduction, 5 minutes, about the next lecture, and then I will follow my approach, that is give this finish a bit earlier to answer questions to those here in the classroom. Let me organize just for a few seconds. Okay. Okay, unfortunately, the monitor does not stream. I wanted to use just my pencil, but technology is not so advanced, so I will use slides, and so that in the recording there will be play. Otherwise, in the recording, this short introduction would have been absent. We will use the schema that you have seen is, of course, an abstraction of the whole process. It is much more more complex, but it's it turns to be useful also for understanding, to making further steps, understanding what are the sources of bias. Let's introduce first what is bias, what definition of bias we are taking into account. Bias in software systems are computer systems that we have bias in software systems when computer systems discriminate systematically and unfairly against a certain individuals or group of individuals, based and assigning them an undesirable outcome on grounds that are reasonable and or inappropriate. For example, due to an optimization that gives more importance to gender, for instance. I propose you, after a full review of the literature that is just here for tracking what were the sources of this schema, I will take again what we have seen, the whole process, to just as a base for different types of biases that we will explain then tomorrow. The first type of biases comes from the people to the data through the measurement process. And this is the very first category of bias. Then the second category of bias is the bias that comes from the data to the model. And then the last one are the biases that goes from the model back to the individuals of groups of individuals. So we have three categories of biases. Biases from individual society to data, biases from data to algorithms, and biases from algorithm to individuals and society. Whatever is here in the data is called the observed space. So it is what we can observe. And comes from, it is called the construct space. What are the theoretical constructs? Productivity is a construct, is a term that is in the construct space, is a concept. Its quantification goes into the observed space. This is important. So first of all, we have a difference between the construct space and the observed space, that is the space where data is. We even have a potential space. How would be the construct space if I were Afro-American, for instance? If I were in another social context? It's called the potential space. And then we have the decision spaces, where decision actually occur. From the observed space is where the data is used to make some classification predictions that in turns come to be decisions that have impact on the people. So going back both to the construct space and to the potential space. We will use this further abstraction built on top of the ML cycle to classify the different sources of data. After having done that, we will move to statistical formulation of algorithmic fairness in order to be able to quantify the disparate impact of an algorithm. Thanks a lot, and we will meet tomorrow in the afternoon. And I will stay, of course, here if any questions are available.